qui utilisent l'éphécoron. C'est vrai qu'il y a beaucoup de progrès dans ce domaine. D'ailleurs, la thématique électrostatique, à 80%, c'est sur l'éphécoron, les décharges. Il y a beaucoup de débauchés et applications industrielles. C'est très avancé actuellement. Il y a beaucoup de chercheurs à l'université de Bijaya qui travaillent sur les décharges coron. Bien sûr, chaque chercheur, il oriente l'étude à sa manière, bien sûr, en suivant l'évolution. Merci.
Merci. C'est bon?
Et il y a d'autres questions? Je vous remercie.
Merci à vous.
Avant de remettre l'attestation à Mademoiselle Chouali, je vous invite tous à la session, à la pause café, à l'esplanade de l'auditorium. Et les chercheurs qui sont concernés par la session poster, je les invite à accrocher leurs posters dans les supports désignés et qui sont en hall. Merci.
Merci à vous.
Merci.
Assalamu alaikum. Good evening, everybody. You will speak in French or in English?
In English.
In English?
Yes.
Okay. Donc, I hope that everyone were well. And I hope everyone here will give some question after listening for your presentation. And to enrich this discussion, I give you 10 minutes, Mr. Babariou Masoud, for giving us the essential of your work entitled Analytical Study on Energy Optimization via Dynamic Transmission Power Adjustment for Offloading in Edge Computing. You have 10 minutes and 5 minutes for questions, eventual questions.
Okay. Thank you very much, Mr. Chair. Thank you everyone for coming here for this session of oral sessions. First of all, I would like to thank you all for being present here and for having me presenting in this prestigious EEIC conference. By the way, this is my second time coming here to Bijaya. I came here when I had only 3 years, and this is my second one. So without further delay, we are going to see a very important topic. I hope that by the end of this presentation, you will get few important things like cloud computing, which is very famous, edge computing, which is one of the trend works of nowadays. You will see a specific problem, and you will see how we could solve it or our proposition. And we are going to do so following this outline. First of all, we are going to see what are cloud and edge, these two paradigms. Number two, system model, our assumptions and the existing problematic. The third one is the taken methodology and simulation runs. The other one is the metrics and results. Finally, we'll give a conclusion. We'll try to be respectful to time because we have only 10 minutes. So number one, cloud and edge computing. So cloud computing, maybe a lot of you hear about this famous paradigm. I will give it in a few short sentences. It's about providing services over the internet. It's like Google Drive, so you'll have storage, processing power, applications, you will get them after going to the internet. It will give a lot of advantages like on-demand resources. So whenever you need it, you just need to be plugged into the internet to get this service. The other one is scalability, because you have only one place and all of you as clients, you can get the benefits of this service. The other one is the accessibility from anywhere. From everywhere, when you have internet access, you can benefit from the service. However, it has some of the drawbacks like latency concerns, because the cloud is too far away. Sometimes this introduces a specific kind of problems that's called delay. The other one is security risks. We can go to the cloud, but also the attackers can do so, either for rivalry or just for disruption purposes, whatever. The other one is the dependence on the internet connectivity. It's true that it's easy to get to the cloud, but if you don't have the internet access, you cannot work or you cannot use this service. This is an illustration, for example. You have the cloud data center, which is the cloud generally, and you have a lot of applications. For example, we as mobile users, we will provide or we will get the service of the cloud via this path. This is for the cloud. I hope that it's clear. Now, moving to another thing, which is the problem. We have statistics, according to The Guardian. It says that 1 in 5 UK children aged 3 or 4 have a mobile phone. What does this mean? And we saw this morning that we have a huge growth of population. So by this growth, the cloud itself, even if it's powerful, it cannot maintain this huge increase in demands. From here, you can expect that edge comes to solve this problem. So what's edge? Edge is like the cloud, but it will gives you the services from another place. You will have not only the cloud, but you will have a lot of servers that are too close to the end user. For example, we will have a server here in Béjaïa University, so it will respond to the clients on behalf of the cloud. This will result in a lot of benefits, like it's a decentralized architecture. We do not have a single point of failure, like the case of clouds. So even if one edge server fails down, you still can work because there is a lot of edge servers. The other one is low latency. We are not going too far away to the cloud. You are just going to the server that's on the proximity of the university, for example. The other one is efficient bandwidth usage. You only use your internet connectivity when you are forced to do so. If the edge server will satisfy your needs, there is no need to go to the cloud. However, there is also some drawbacks, like limited resources. You cannot maintain a huge coverage of edge servers because they are not too powerful. So to replace the cloud, you need a lot of edge servers, which is not practical sometimes. The other one is security challenges, because you need to maintain every single edge server. You need to provide its security updates and so. The other one, or the last one, is the integrity complexity, because you need to deal with a lot of heterogeneous devices and brands. You need to ensure that the application that runs on the cloud, it will also run on the edge server, which is challenging. This is another illustration of the edge paradigm. We have our clients, we have the cloud data center, and what you remark here, it's located in between, so it will respond on behalf of the cloud if necessary. Another remark that you can get is that they are working all together. So if we plus cloud and edge, there is no such of a comparison between which is the better one. The answer is edge is a complement to cloud. So I'd rather like to give you some edge applications to give you into the picture. We use edge in a lot of scenarios, like in robotics, when you have a production line, you have to remove the bad parts and keep the good parts. It needs a very short time for decision. So the robot needs to pick it so quickly. The other one is in drones and vehicles. So the vehicle needs to decide whether to turn left or turn right in real time. So it will not ask the cloud, rather than that, it will ask the edge server. The other one is in surveillance cameras. So to make facial recognition, you need to make it in a very short period of time. The other one is in augmented reality. The edge server will run the artificial intelligence on behalf of the cloud, because generally we use it in the cloud. The other one is in gaming, because a lot of players who know this word, about the word lag, so to reduce the lag, the freezing time, we use edge. The last one is in farming field. So these robots are also involved in making farming and so, an agricultural field. The last one, sorry, is in satellites. So the satellites can act as edge server. If you are in an isolated location, so the satellites will behave as edge servers. So now let's draw our system model, which is the assumption, and we give the problematic. So for our assumption, we use the following model, where we have the mobile edge devices, that are the clients. We have also the access points, the points that will be the path between the mobile devices and the edge servers. The other one is the routers, if we are going to another network or subnetwork. The edge servers, our main actors. We have the brokers. The broker, by the way, or sometimes called the orchestrator, is a device responsible for delivering the task to the appropriate edge server. Because we have a lot of edge servers, and we have the clients. So to put a client into an edge server, we need this component, which is the orchestrator or broker. The other one is the cloud data center. This is indispensable We said that it's a complement, not a replacement. And we have a radio medium. We are sending these packets wirelessly. We should take it into consideration. The last one is the offloaded tasks. The task is the operation that the mobile user wants to accomplish. And offload, by the way, this word means the operation of sending a task to the edge server or to the cloud. We call it offloading. So, for the existing problematic and remarks.
Please, there is less than 1 minute.
Okay, no problem. I will accelerate things. So we can remark that the mobile devices have limited battery lifespan. Of course, this is obvious. The other one, making losses, local processing consumes a lot of energy. Why we are sending the tasks to the cloud or the edge? Because our devices do not have enough energy. The third one is sometimes, like in this room, we have a lot of mobile devices and we have an access point that's too close to you. With these three remarks, we will proceed to defining our methodology so quickly because we are running from time. So some environments like this one is dense, having enough and close access points. Mobile devices support location awareness. They know that the device is too close to them. Sending with minimum transmission power, this is our assumption. We assume that we can maintain different kind of transmission powers, which means different transmission ranges. With this one, we proceeded into defining our table. So depending on my distance to the edge, to the access point, I will change my transmission power, okay? So for the consumed energy, this is a very simplified formula, where the consumed energy equal transmission power, of course, multiply by the time, the duration when I'm sending the packets or the tasks, plus the size of the task multiplied by the energy consumed by sending 1 bit. This is very simplified, by the way. There are some other complicated things. So we'll proceed directly to the simulation. We choose 1 task per second. The application used is MQTT. I will not dive into this because of time. It's used in IoT devices. Transmission power levels, we choose four of them. The map is 400 meters square. Simulation time, we took 5 minutes. For the mobility, we used a linear mobility model. This is an illustration of the conducted simulation. For the metric and results, we choose only 2 metrics. The first one is the number of transmitted packets per type. We said that there are 4 transmission powers, so 4 transmission types. And the consumed energy percentage. For the first one, we remarked that in a scenario like this one, we could achieve a lot of transmission power with a very low transmission power, which means that the access points were too close to them. Generally, in the normal mode, we will still transmit with the maximum power, which is not feasible for our case, which is the energy draining. For the consumed energy, here is the percentage. So if we do not use our scheme, we got this blue line. But after applying it, we got a very high reduction in the consumed energy. So as a conclusion and summarization, we saw what cloud is and what edge computing is, these 2 paradigms. We also saw that we have a limitation in our mobile devices, and we saw that changing transmission power is very favorable for the energy constraints. The other one is the different chances of reducing the transmission power. We saw that there are some occasions or the chances to reduce the transmission power. So that is it, I guess. I would like to thank you very much for your attention, and sorry for exceeding the time.
Thank you, Mr. Babayu.
You're welcome.
If there is any question, please do.
So, thank you for your presentation, Mr. Babagayu. Yes. We didn't have time to follow because you went very fast. Exactly. Can you please go back to the slide where you showed your methodology?
Sure.
So,
So here is the methodology section.
Okay. So you are sending. So basically, you are considering one access point.
4 access points in the simulation that we conducted. It's just an example that I showed you.
No, just for your simulation.
Yes, for my simulation, there are 4 access points, yes.
Okay, and users are close by. Like
exactly, randomly, yes.
Okay, and how do you separate from the access point, for example? How does it know that this data should go to this user and this data should go to that user?
Okay, I'd rather give you the figure to get a better discussion. This one, yes? Mm-hmm. So, you're asking me how can the access points know to reply, for example, to this user? Let's take this example.
When the access point sends the data to the user.
Okay. At first, the user sends the data to the access point.
Okay, then how does the user know which access point to contact?
We said that it has a location awareness. We assume this during the assumption. So the user knows the location of every access point.
And it will contact the one that's
closest. The closest one, exactly. Okay. It's already implemented in the simulation.
Okay. So when the access point, let's assume you have like 4 users, 1 user per access point.
Yes, we have 100 access points.
Let's just from my question.
Let's assume. Okay.
So if we assume that the 4 access points are sending at the same time to user 1, like access point 1 to user 1, access point 2 to user 2, access point 3 to user 3, access point 4 to user 4. Is it directed to the user, or does the user receive everything and then take the signal that's targeted to it?
No problem. This is related to networking in general, if you want to explain it as networking. So when the user sends the data to the access point will maintain the connection. Okay. Let's give you an example in your router in your home. So when you are using a private network, so there is like NAT. It's make NATing. Mm-hmm. So it will add a port, a local port, and a public port. The public port is used to contact the cloud or the edge. Mm-hmm. They use the same principle. So when the access point, the cloud will contact your router. And your router will make the decapsulation. There is encapsulation and decapsulation. Based on this port, it will send it to the appropriate user.
So it has like a wireless port?
It's like wireless access points, yes.
No, just the port is wireless.
Port, it's something logical, by the way.
I mean, it's not related to the user through cabling. It's wireless.
It's wireless. It's wireless. I'm talking about another kind of ports. It's in networking. Okay. It's like a field in the packets, somehow. Okay. And I don't fear to tell the router or your router that this is the point of connection to the end user.
Okay, so just to make my question very simple.
Yes.
Do you have a problem of interferences in edge computing or not?
There is interferences at the level of broadcasting these packets. Yes, this phenomena happens in everywhere, not just in this case scenario. But since we are using wireless medium, there is this kind of problem.
You don't consider it for your research?
I didn't consider it. If you remark, we have only broadcasting with 1 packet per second. We're trying to see the charge. We are overcharging the edge servers, but not the medium. Okay. This is a global problem. I agree with you. Yeah.
Thank you. Very good presentation.
You're welcome. And very good questions. They are good debate. Thank you.
I have one question. Is there any latency concern if you are using the 5G technology?
Okay, for 5G works perfectly with edge. They are like, there is a synergy between edge and 5G. Why is this? Because generally in 5G, we put edge servers close to the access points, to the we can say access points, yes. So with 5G, with the high bit rates and bandwidth, it works very well with the edge. Or what was your question exactly?
Is there any concern about the latency?
In 5G, I mean?
Yes.
Okay, 5G alone reduces the latency.
How?
How with high bandwidth. You know that it works in a high frequency, so it will deliver a lot of data at a very short amount of time. This, as a consequence, will ensure that your data arrive so quickly.
But which techniques is used for this?
For 5G?
Yeah.
I'm not aware about it, but as far as I know, it provides a very high bandwidth and a very short latency. So
The technique is,
yes, of course.
the technique is the slicing. If you know what
Yes,
is.
I heard about it.
Okay.
Slicing. Yes.
That's reduced latency.
It's using a brand of frequencies.
The edge computing consists of putting the server at different level, and the approach latency will be reduced when the transmission and the reception will be the distance between the access point, user or radio, and the server. We compute this virtually and put it for different applications.
So 5G,
You have said for vehicular. We need a very
low latency.
Yeah, latency. That is an example.
Okay. But this is between the 5G access point and the mobile user, isn't it? The slicing technique.
Yes, in a RAN.
In RAN, and random access network.
No, in the RAN, radio access.
Radio access networks. Yes, I know.
Yeah.
I know. Yeah. So, but still, there is a connection between the RAN and the edge server.
Yeah.
So
the latency is also exists also in the core. A core network.
In the core network,
yes.
Yes,
between the Ethernet.
Yes.
And the network of operators.
Exactly. Yes. So we can say it's the sum between this one and the link between the user and the RAN.
Exactly.
Yes. Thank you very much for this remark.
Never mind. You're welcome. Thank you.
كيفاش طفي
Mr. Babayu, please, you will give you your certificate.
The second speaker is Monsieur Bikanaj. He will tell about our topic is titled Performance Analysis of Spatially Modulated MIMO Systems. Monsieur Bernaj, you have about 10 minutes. Okay. If you want to speak French, you can do it. Okay? You have the choice.
Ladies and gentlemen, dear guests, research and enthusiasts of the new technology. It's with immense pleasure we are assembled here today to present my paper entitled Performance Analysis of Spatial Modulation MIMO System. Allow me to present you the outline of my presentation. I begin with introduce. The second point, system SM MIMO. Last, simulation performance SM MIMO, and I conclude with a conclusion. Nowadays, wireless communication plays a major role in our society, increasingly integrating into our electronic system around us. Consequently, the demand in terms of speed and reliability are consequently expanding. To cope with performance requirement and propagation channel impairment, various techniques have been proposed in the literature, such as a cognitive radio and SM MIMO system. As for the objective, this presentation highlights spatial modulation as an innovative alternative to convolutional MIMO system. By reducing radio frequency cost and SM MIMO provides significantly advantage for emerging wireless communication system. We explore recent advancement and motivation for the widespread adoption for SM MIMO. The concept of MIMO, one of the most innovation technology used in radar wireless networks and mobile networks. Introducing spatial diversity significantly reversing the throughput and robustness of wireless networks, achieved through the deployment of antenna area. It allows for improving the signal-to-noise ratio and ensuring transmission reliability by reducing the probability of error, thereby increasing throughput. The concept of MIMO system, transmitter and stream using an antenna at the same time, forming matrix H as shown in the figure. The reception algorithm, ZF, zero forcing, the simplest linear receiver. There are for the removal of the information element, and he inverts the transfer matrix. Minimum mean square error minimizes the mean square error due to noise and EOS. Maximum resemblance, it's the optimal in terms of bit error rate. It is based on the creatures that minimize the noise power on the receiver vector. The second point, spatial modulation. There is innovated and applying digital transmission technique with multi-put and multi-out MIMO, allowing increasing transmission speed and reducing the system complexity. In single-user SM, only one transmitter is active a given time, while the other remain silent. Information bits are divided into two blocks in two parts. A block containing a unique transmitter antenna number, referred as the antenna index. The second block containing the information bit transmitted by the convolutional symbol of the constellation PSK, and QAM. This figure illustrated a block diagram of an SMMO transmitter consisting of two input blocks and a signal active antenna with a single radio frequency, as explained earlier. In the reception, SMMO utilized two-step algorithm approach. The first step involves detecting the antenna index, and the second step is the sample detection. There is an example for the modulation spatial. An example of coding spatial modulation SM. The bit block to be coding is 1110. The first two bits, 11, determine the active unique antenna, TX3, while the last 10 determined the transmitter PSK QAM symbol. That you show this. Moving to the simulation now. We have an SMMO system under two modulation schemes, PSK and QAM, and then we have compared its performance in terms of BER, capacity, and spatial efficiency. We begin with BER. The figure depicts that the bit error rate for QAM and SPEC increased as we increase the modulation order, represented by M. Analyzing the presented result, it is observed that the capacity decreased with M, modulation order. We observe that by increasing M, the spectral efficiency increases significantly. The second part, we configure the antenna. Increasing the number of antennas in both transmission and reception leads to a decrease in bit error rate. We observe that the performance degrades as the number of antennas is reduced. By varying the number of antennas and analyzing the presented result, we observe that spectral efficiency increased linearly with the number of antennas. Conclusion. The research provides a solution to improve the performance of MIMO system by incorporating spatial modulation technique. Simulation results show that SMMO system outperform in terms of transmission capacity, bit error rate, and spectral efficiency. The performance of PSK is superior to that of QAM in certain scenarios. This suggests that the proposed solution can lead to significant improvement in the performance of MIMO system, particularly when using PSK modulation technique. Perspective, suggesting algorithm for the recognition of the other parameters coding at the number of antennas. Thank you for your attention.
Thank you for your presentation. I will pass directly the word to the assistants if you have any question.
Je préfère pour que l'assistance puisse suivre, les questions seront en français.
Est-ce qu'il y a des questions? Allez-y, monsieur Tounsi.
Oui, alors, déjà je les félicite déjà. Je leur dis bonjour à tous les étudiants de Master 2 de L3 qui sont là avec nous. Oui. Parfait. Alors, donc, si on parle de MIMO, donc c'est multiple in, multiple out, c'est la transmission de n flux d'informations sur n antennes. C'est-à-dire, on peut envoyer sur beaucoup d'antennes et recevoir sur beaucoup d'antennes. Donc, la radio spatiale, qu'est-ce qu'elle ajoute? Donc, c'est pour réduire le nombre de radiofréquences. Déjà, donc si on réduit le nombre de radiofréquences, déjà, donc le coût sera moins. Et même on va gagner question d'énergie, puisque la radiofréquence, puisque la modulation spatiale, mais l'antenne qui est active, elle met l'antenne qui émet ou bien qui reçoit active, tous les autres antennes seront silencieuses. Donc déjà, on gagne en coût d'énergie. Deuxième, comme j'ai dit auparavant, donc en termes de radiofréquence, tant qu'on élimine, enfin, on utilise moins de radiofréquences, donc on gagne aussi en termes de coût. Pour troisième question, je me rappelle pas. Oui, donc les égaliseurs ici, on les a utilisés pour dans la réception. C'est des algorithmes de réception qu'on a utilisés ici. Donc, on a utilisé le MMSE, maximum, l'erreur quadratique moyenne. Donc, c'est grâce au MMSE qu'on a pu avoir ces résultats-là. Voilà.
Merci, M. Benedj. Est-ce qu'il y a d'autres questions? Sinon, je vais en poser.
Ben oui.
Donc, vous avez cité le ZF, l'égaliseur.
Oui, zero forcing.
Oui.
Oui.
Quel est son défaut?
Alors, dans le zero forcing ici, donc je l'ai juste mis à titre de littérature, mais dans la pratique, j'ai utilisé le MMSE. Donc, zero forcing, je l'ai lu juste de manière générale. Donc, on a travaillé sur le MMSE. C'est juste pour montrer les algorithmes de réception qu'on peut utiliser. On peut utiliser le maximum vraisemblance, le ZF et le MMSE. Donc, dans notre cas, on a choisi d'utiliser le MMSE. Voilà. Donc, je ne peux pas répondre puisque j'ai pas...
Il n'y a pas une étude comparative.
Non, on n'a pas fait une étude comparative. Donc, ici, donc, on a fait l'évaluation des performances. Donc, il n'y a pas d'étude comparative. C'est juste, on a fait des petites comparaisons entre deux modulations, que ce soit PSK ou bien QAM. Et c'est ce qu'on a... on a déduit ici, donc, dans notre simulation, que les performances de PSK étaient supérieures à celles de QA. C'est ce que montrent les résultats de simulation.
Comme schéma de modulation, vous n'êtes pas monté, vous avez juste utilisé QAM, pas 16 QAM, pas 64.
Enfin, on a fait deux.
Ou 8 PSK, ou bien.
Oui, alors, donc ici, donc, comme vous voyez ici, dans la simulation qui est ici, voilà, on va juste la montrer. Voilà, ici, donc, on a varié les ordres de modulation. Donc, on a le 2, le 4, le 8, le 16 et le 32. On a gardé les antennes émettrices et réceptrices fixes. Donc, on les a fixées à 8. Donc, on a 8 antennes réceptrices et 8 antennes émettrices. Et on varie l'ordre de modulation. Dans la deuxième partie de notre configuration, on a fait le contraire. On a fixé, voilà. Ici, par exemple, on a fixé l'ordre de modulation à 16. Et on a varié le nombre d'antennes émettrices et réceptrices. Donc, le premier, par exemple, c'est 2, 4, 8 et 16.
D'accord. Donc, si vous revenez à la première figure, s'il vous plaît.
Bien sûr. Celle-ci?
Voilà.
Oui.
Donc, on voit bien qu'ici, en augmentant le SNR,
oui.
D'accord. Donc, c'est normal que le BER diminue.
Oui.
D'accord. D'autant plus que si on est en modulation 8 PSK, je pense que c'est celle-là qui donne le meilleur résultat, non?
Oui, alors ici les résultats montrent que...
Oui, c'est la 8.
Oui.
La 8 oui, 8 PSK.
Exact.
Fast Shift Keying. La question, est-ce que ces résultats, ils sont utilisables?
Alors, donc, c'est les résultats qu'on a eu de nos simulations. Alors, sur le cas pratique, enfin, je ne sais pas exactement. Mais
Ils n'ont pas,
donc,
effectivement, ils n'ont pas atteint, c'est-à-dire pour qu'elle soit implémentée, il faut que ça atteigne au moins 10 puissance moins 6,
oui,
comme bit error rate.
oui, enfin, ici on a pu arriver jusqu'à 10 puissance moins 6.
C'est ça, oui. Donc, difficilement. Hein,
oui.
Parce qu'en implémentant, ça change, la pratique, ça change.
Ben, c'est normal, oui, c'est tout à fait normal.
Pour le zero forcing, c'est juste pour vous dire que son véritable problème, c'est le bruit.
Très bien.
D'accord. Parce que le zero forcing, il est très très simple à mettre en œuvre. Son problème, c'est quand vous inversez, parce que c'est la base d'inverseur. Quand vous l'inversez, donc tout ce qui s'annule devient infini. Donc le bruit 1. Donc j'imagine que vous avez compris. Merci, M. Prénet.
Merci beaucoup, merci à vous.
One, two, okay. نعم. شو الجملة؟ Okay.
Mr. Wajiz, are you ready?
Always. Good afternoon, ladies and gentlemen.
I don't introduce you. I will introduce you. Then you will present us your essential of your work entitled Numerology, Interference Analysis and Mitigation Techniques for 5G Networks. You have 10 minutes. Please don't.
So good afternoon, ladies and gentlemen. My name is Yassin Waziz. I am a PhD student here at the University of Bijaya. I am currently working on a thesis aiming to optimize the radio resources sharing in 5G networks. And today I'm going to be talking to you about internumerology interference, which is a pretty technical concept, but I'm going to try and make it as simple as possible. My presentation will be organized as follows. So I will begin by briefly introducing to you the 5G networks, and then I will move to the concept of multinumerology, which lead to internumerology interference, which we will analyze together, and then I will cite or mention some any mitigation techniques that have been applied by the literature, and then I will suggest some future research axes before concluding. In the beginning, 5G came with many challenges. It was put in application due to the increase in demand of the users and the customers, and it came with many objectives. To summarize it, it came in order to be 10 times better than 4G in pretty much everything. So it is supposed to achieve 10 times higher throughput, a 10 times lower latency, and a 10 times higher connection density. Along with this and many other challenges, if we take them all together, they seem impossible to reach. So 3GPP decided to divide the problems into three major use cases or families. EMBB, standing for Enhanced Multicast Broadband, which is designed for applications that need a very high throughput, such as virtual reality or Ultra HD videos. URLLC is standing for ultra reliable low latency communication, which, as its name indicates, is designed for low latency and so for applications that require a very low latency and a very high reliability, such as autonomous vehicles or remote medicine. And the third one is MMTC, for massive machine type communication, which is designed for smart cities where we have a very dense population. So all of this has been made possible by network slicing, which Mr. Belhassan mentioned earlier, and this technically has been made possible by what we call multi-numerologies. In order to understand that, we need to know that in radio networks, the frame is based on what we call a resource element. What is a resource element? It is a certain frequency band called subcarrier spacing and a certain time slot in which each symbol will be transmitted. So in 4G, SCS was fixed to 15 kilohertz and the time slot duration was fixed to 1 millisecond, meaning that all the users would transmit according to that. In 5G, many other numerologies have been introduced, as it will be depicted by this table, which we don't have time to read thoroughly, but if we take, for example, the example of numerology where mu is equal to 2, the subcarrier spacing has been multiplied by 4, allowing us to reduce the time slot duration also by 4. So it allows us to like allocate to each user the exact amount of resources that they need. That's like globally. Okay, we unfortunately don't have time to go into details. And this allows a high flexibility to the network, but it comes with a big drawback, which is internumerology interference, or INI. In order to understand that, let's consider a system model with two numerologies, so numerology 1 and numerology 2, and we consider a scaling factor, which is the ratio between the two numerologies. For simpler calculus, we're going to consider it's equal to 2. So for example, we talk a delta F1 of 30 kilohertz and delta F2 of 15 kilohertz. Okay, and then we consider that symbols are generated, modulated by, like QAM modulated, and then transmitted via what we call subcarrier phase, which is just an exponential function at the desired frequency. So in order to understand what interference between subcarriers is, we need to calculate the correlation between them. Given by the following example, by the following equation, it's really just an inner product, very simple math. It's just an integral on the period of the product between the two subcarriers. We're not going to go into the details, but what we need to know is that in a single numerology, the two subcarriers from the same numerology are orthogonal to each other, meaning that the correlation is equal to 0 and they don't interfere with each other. That's the principle of OFDM transmission. But with different numerologies, the correlation between the subcarriers can be given by this equation, which is 1 on the square root of V of times the sinc function of a factor D, which refers to the relative distance between the two subcarriers, subcarrier M from the numerology 1 and subcarrier N from the numerology 2. It is given by this equation, which is just the rank of the subcarrier M minus N on V. Okay, let's look at the drawing of this correlation in order to try and understand better. We have simulated and plotted the correlation between the subcarriers against the relative distance between the numerologies, and we have varied the scaling factor. So in blue, we consider, for example, the case where numerology 1 is equal to 30 kilohertz and numerology 2 is equal to 50. And then we took numerology 1 to 60 and we kept numerology 1 to 50. That's just so, in order to summarize what this figure shows, we see that for direct neighbor numerologies, where the scaling factor is low, the correlation is very high, and it gets lower as the scaling factor increases, and it gets also slower so the more distant the two subcarriers are to each other. So this can still be a little complicated, but we're going to make it even simpler by considering the frequency domain. The frequency representation of OFDM signals is a simple sinc function. Where the subcarrier spacing is equal to 15 kilohertz, we have perfectly aligned symbols, and when the symbol is at its peak, that's when it transmits. All the other signals are equal to 0, meaning that they don't interfere. With multiple numerologies now,
So when a symbol from numerology 1 is at its peak and it transmits, all the symbols from the same numerology are equal to 0. But the symbols from the other numerologies are still existing. That's what we call INI. I hope I made it clear, because now we're going to see what mitigation techniques have been applied by the literature. So I'm just going to really I'm not going to go into detail, but this is a very recent research topic and not a lot of works have been done. But up to now, the researchers have been applying what some deep reinforcement learning methods, some various methods for interference analysis and cancellation, such as non-orthogonal multiple access, which produced pretty good results, but they only take into consideration the bit error rate and the spectral efficiency, which is, I guess, okay, but they didn't consider what is supposed to be one of 5G's challenges, which is the latency. Because when you use deep reinforcement learning, for example, of course, it's a very good technique, but it also takes a lot of time. So I think that in the near future, researchers should maybe focus on developing interference techniques that are more tailored for INI, not just take interference cancellation techniques from other cases and apply them to INI, because this is a very particular case. And, just develop efficient resource allocation algorithms and scheduling schemes that would actually consider the user requirements, traffic patterns, and channel conditions. So not just take something and from somewhere else and apply it to INI. Because if we take a look at the, if we take a look at the spectrum, we see that INI only occurs on every other symbol. Not all symbols are affected by it. So that's one point to consider in order to make these techniques more efficient. To make the long story short, in this presentation we have introduced to you the concept of multinumerology in 5G, which came with its set of problems, so internumerology interferences, which we analyzed, tried to explain. I hope I made it clear. I tried my best. And, we have mentioned some mitigation techniques. We have mentioned some future research. And we are really, we lay the groundwork for addressing the complex challenges posed by INI in the 5G network. And we really cannot emphasize enough on the importance of continued exploration and innovation in this topic. Thank you for your attention.
Thank you, Mr. Waziz. Without latency, questions, please.
Questions?
Yes, Mr. Tunsi.
Alors, pour ceux qui n'ont pas entendu, M. Tounsi vient de demander pour quelle catégorie d'usage on accorde une importance plus grande aux interférences. C'est ça? OK. Donc, on a en 5G, ça c'est applicable un peu partout. Et chaque application a ses propres requirements, a ses propres exigences. Donc, INI, l'interférence internumérologie, ça affecte surtout le bit error rate et l'efficacité spectrale, parce que je peux pas remettre malheureusement, mais si on regarde, une idée simpliste serait de dire on éloigne juste les deux numérologies, on n'aura pas de problème d'interférence. Oui, mais on va gaspiller le spectre qui se trouvera au milieu. Et ça c'est pas acceptable. Mais pour ce qui est des applications les plus importantes, c'est très subjectif comme question, parce que tout le monde a ses préférences. Pour moi, par exemple, si vous me dites, pour moi, ce serait dans URLLC, dans Ultra Reliable Low Latency Communications. Parce que si j'ai des interférences là, et qu'il y a une voiture qui se conduit tout seul, si elle a besoin de freiner, et si j'ai un temps de latence, elle freine trop tard, j'ai accident. Si j'ai médecine à distance, J'ai un chirurgien qui fait une opération à distance, je ne peux pas me permettre d'avoir une erreur binaire, parce que si j'ai des bits qui se trompent, au lieu de toucher le cœur, il peut toucher un poumon. C'est juste un exemple. Donc pour moi, je pense que c'est, en tout cas, ce sur quoi je me base, c'est les communications à faible latence et à haute reliability. Maintenant, je pense que tout est important et il y a vraiment, comme on dit, à boire et à manger dans ce sujet. Donc, il y a des améliorations à apporter partout. Si je me focalise sur l'URLLC, quelqu'un d'autre peut se focaliser sur EMBB ou MMTC, par exemple. J'espère que ça répond à votre question.
Est-ce qu'il y a d'autres questions? Oui. Yes.
Mm-hmm.
How about the frequency that's used? Does it make some endangering life?
Does it endanger life?
Yes, because it works in a high frequency.
Yes. That's a very sensitive question, because I work on 5G. If I say yes, I have nothing to work on. But let's take this, like, do you know that, let's say, for example, the microwave. Can you imagine yourself in a microwave? You would explode, right? So 5G is closer to the microwave than 4G. But in my opinion, we are still far enough away to be safe. But we're getting there because in 6 generations, they're moving to terahertz, okay, which will get closer. For 5G, for now, I think we're safe, but I'm not a doctor. What's your other question? Mm-hmm. So you mean range like the distance with the user? Okay, so of course. So as you know that.
Please, can you repeat your question, please?
Range. So he wants to know if there is a correlation between the frequency that we use and the distance that the antenna can reach. Okay, so you know that the wavelength lambda is given by C on F, right? With the speed of light on frequency. So the higher the frequency, the lower lambda, the lower the wavelength. Okay, and the lower the wavelength, the lower the range. Okay, so as I increase the frequency, I decrease the range, but I improve the throughput. Okay, I don't think we have time to really get into detail because that's a very interesting topic and that's my passion. But you know, we can exchange our numbers and discuss. Mm-hmm. Mm-hmm.
I don't think that delay will cause faults.
Well, sorry, I'm sorry to.
Okay, you give an example that if we have a high delay, so instead of touching the pads, you touch the key.
No, sorry. I gave the delay example for the autonomous car. Okay, so for autonomous car, I'm getting there. So for the autonomous car, when I hit the brake, I need the car to stop right there. That's when I cannot afford delay. For the remote surgery, I said we cannot afford a high bit error rate.
Yes.
Okay?
But there is a control of error, so there is it will ask for a retransmission.
Yes.
It will not affect the action, I believe.
So it will ask for a transmission. How many times can you ask for a transmission? Exactly. So what we are aiming is to reduce the interference. So maybe at some point the first transmission will be okay. You know what I mean? So I'm not getting into the detail of informatics. Okay, I work on the physical layer of the ISO model. Okay, I only work on the bits and the transmission. What I'm aiming for is for the bits that I send, for the bit error rate that I send, for the bits that I send to arrive as safe as possible. Okay, so I cannot afford the bits to be changed.
I agree. And from the computer science perspective, I said that I believe that the action will not be it will not take another action. So if you have an error, bit error, it will not impact the actions the device will take.
But the device speaks in bit. What if half the bits it receives are fake? How about if the second time, for the second retransmission, it gets a 40% bit error rate? Then it will ask again. So I'm losing time. Yeah, exactly. So we are aiming to reduce the bit error rate. That's what we're doing. We agree on everything, my friend. Thank you.
Donc, si on résume un petit peu, donc si vous avez la question que vous avez posée, c'est-à-dire que Monsieur Aziz, il parlait d'une erreur en cas il y a une grande distance, c'est-à-dire il faut imaginer qu'il y a un chirurgien qui se trouve en Australie et vous avez quelqu'un qui se fait opérer en Allemagne, par exemple. Donc, il y a les deux, au fait. Il n'y a pas que l'erreur. Il y a la latence. Ça ne peut pas attendre parce que c'est robotisé. J'imagine que vous avez une idée. Donc, c'est robotisé. Il fait l'intervention, il se trouve ailleurs. C'est le seul qui peut la faire. D'accord? Donc, la latence, il faut qu'elle soit vraiment réduite. Et en même temps, l'erreur, elle est impardonnable. Yes, I know. Okay, thank you.
But it's clear now. Perfect.
Okay. Monsieur Ouaziz, je déplore un petit peu qu'il n'y ait pas assez de graphiques pour illustrer l'idée pour la faire sortir. Mais j'ai une petite question.
Oui.
Concernant what about when you have a weak interference and you have strong interference? When you have, example, you have cited OFDMA. OFDMA, it's orthogonal.
OFDM what?
OFDMA. L'OFDM. OK? Donc l'OFDM, c'est une technique orthogonale.
Oui.
Qu'est-ce qu'on peut dire des techniques non orthogonales dans ce cas? Parce que c'est ça ce qui est en train de se faire actuellement.
Les techniques non orthogonales.
Que ce soit SDMA, NOMA, RSMA, voilà,
Exactement. Je pense que c'est un axe de recherche intéressant à explorer. Parce que ça a déjà été fait, NOMA for 5G networks, for internumerology interferences. Le point négatif qui est venu avec ça, c'est que ça a affecté la latence. Parce que when I do the successive interference cancellation, it takes a lot of time. And sometimes I cannot afford that in 5G. That's the problem. C'est ça. Je suis bon, Cheikh Khawat.
Thank you, Mr. Aziz. Allez-y, monsieur Tounsi.
Dangerosité de 5G. Est-ce qu'on y est? Tu fais en français? Ah, il est bien. Pour l'abattre. Vous êtes d'accord?
Merci, Monsieur Toussi. Je vous remercie parce que ça me permet de rebondir. J'ai oublié la question qu'il a posée, en fait, à propos de la dangerosité des hautes fréquences, effectivement. Donc, mais il ne faut pas oublier un paramètre. Parce qu'au début, les portables, ils étaient entre une consommation power entre 2 jusqu'à 8 watts. Actuellement, plus on monte en fréquence, plus la puissance diminue. Actuellement, on est au nombre de 0,2 watts. Donc, c'est ça l'argument qu'avancent, entre guillemets, les industriels pour contrer la dangerosité des ondes électromagnétiques. Parce qu'on est dans les millimeter wave, effectivement, en 5G. Donc, on arrivera bientôt au terahertz wave pour la 6e génération, ça c'est clair. Mais ce qu'il y a, c'est qu'on vous dira toujours que la puissance, elle a diminué. Donc, même si on augmente en fréquence, la puissance diminue et les ondes vont devenir plus directives. C'est-à-dire, elles vont arriver à l'échelle du laser. Donc, c'est-à-dire qu'elles ne toucheront pas d'autres appareils, elles toucheront que l'utilisateur concerné pour lui fournir le débit qu'il veut. Voilà, juste une précision. Merci. Merci, Monsieur Aziz.
My pleasure. فوتوغرافني ديال عائلة انت لمسك ميرسي مسيو كم بالله غير Merci, merci à Cheikh بارك الله فيك, merci pour tout. Magnifique. بيضها فرصة.
Salam alaikum. On vous remercie, Monsieur Ouaziz, pour votre présentation. Elle était très, très intéressante. Votre intervention, on a clôturé avec quelque chose de top. Merci. On va clôturer les travaux de la 2e conférence internationale pour le premier jour, le jour du 5 décembre 2023. Demain, Inch'Allah, donc on va continuer. Nous aurons 2 sessions orales qui sont programmées et une session poster. Et puis, je tiens à remercier tous les communicants qui ont exposé, que ce soit des présentations orales ou posters. Je remercie aussi notre comité scientifique qui ont présidé les sessions. Nous remercions tous les participants de la conférence EEIC'23. Et demain, Inch'Allah, j'espère que vous serez toujours là. À demain, Inch'Allah.
Test.